So today I'll be talking about a recent preprint on selective control of conductance modes and multi-terminal Josephson junctions. So this work was done in collaboration with people at UCSB, and the fabrication for these devices was done at Minnesota Nanocenters. And yeah, this work was funded by NSF, Division of Material Sciences. So I'll start by giving a brief outline of the talk. So first, so the main motivation behind this work is to uncover or detect the Andreev bond state spectra formed in multi-terminal Josephson junctions. And so I'll describe the device architecture that we used that can potentially allow us to study these Andreev bond states. And then I'll describe the transport properties of the devices that we made. And in the end, I'll demonstrate that we can control each of the terminals of a three-terminal Josephson junction selectively, and show that we can access the single mode regime between all terminals of this multi-terminal device. So I'll start by describing what are Andreev bond states. So the Andreev bond states can be understood by first talking about Andreev reflection. So if you have a normal metal that is in contact with an insulator, and if you have electron propagating from normal metal towards the insulator, they get reflected back. You get no transmission inside the insulator because it's an insulator. So, but the situation changes drastically if you, instead of an insulator, you have a superconductor. So if you have electrons incident from the normal region onto the superconductor, because of the coupling present inside the superconductor between electron and holes, this electron can get reflected back as a hole while transferring a charge of 2e inside the superconductor. So this process is known as Andreev reflection, and this process is allowed, and it does happen. So now one could imagine placing another superconductor on the left of this structure. So now when the electron that got reflected back as a hole can get reflected back as an electron again, and then the electron could get reflected back as a hole again. So this process could continue on perpetually, and one could think of this electron hole quasi-particle as a bound state between the two superconductors. So this is known as an Andreev bond state that is formed in this SNS structure, which is also known as a Josephson junction. So one could then talk about the spectrum of these Andreev bond states. So the situation is quite similar to having an electron hole particle stuck inside a finite potential well of height between the two superconductors that are characterized by their superconducting gap delta and their phases phi1 and phi2. So it's the phase difference that's the gauge invariant quantity here, which also plays the role of quasi-momenta for this Andreev bond state spectrum. So then one can evaluate this energy spectrum epsilon of phi as a function of phi. And so here's the energy spectrum for a two-terminal Josephson junctions with a finite transmission. So this is the Andreev bond state spectra for a two-terminal device. So similarly, one could evaluate this thing for a multi-terminal device. So here, if you have n superconductors connected to each other via the scattering matrix S, then the Andreev bond state spectra would be n-1 dimensional. So we already see that this spectrum is not bounded by 3 dimensions as a conventional material would be. And the other interesting property of this Andreev bond state spectra of multi-terminal devices is that they can realize this topologically non-trivial phases. So here is an Andreev bond state spectra for a 4-terminal device with 2 of the phases fixed. So this is Andreev bond state spectra plotted as a function of phi1. So this spectrum looks good. There is nothing not normal about it. So if we were to change phi2 and phi3 such that the spectrum crosses 0, then this 0 crossing happens as a while node. And when this spectrum crosses this while node, it enters this topologically non-trivial phase. So we see that this spectrum is not bonded to 3 dimension and can realize this topologically non-trivial phases. So the next question that then one can ask is, how do we detect this spectrum in an experiment? So if we were to talk about the topologically non-trivial phase, then in a transport experiment, this non-trivial phase could appear as quantized transconductance and vanishing direct conductance. But this has a strict requirement that the number of conductance modes that you have between any pair of terminals is 1. Otherwise, this signal is not detectable. So that's the first condition. The other experiment that one could do is a spectroscopic experiment, as has been done for two terminal devices, where you attach a tunnel probe onto the normal region. So here the normal region is this thin wire-like structure, which is a carbon nanotube. And the Josephson junction is formed by this green fork through which you can thread a flux phi. So one could do an experiment like this, where you have this tunnel probe attached to the normal region. And then one can evaluate this tunnel conductance that allows the calculation of density of states. So one can see these resonances in the density of states as a function of energy. And these resonances can be interpreted as the Andreev bond states that are formed in this carbon nanotube. But again, this experiment also requires that the number of conductance mode is very less, because otherwise you will not be able to resolve these subgap resonances. So just to summarize, what are the necessary requirements for this detection of Andreev bond states in a multi-terminal device? So one would want phase coherent transport, because it's the phases that play the role of this quasi-momentums. And we would like to control the number of modes for each terminal, so that one can tune this Andreev bond spectra formed in MTGHs. And we would like to access the regime of few modes along with the superconducting coupling present. So in this experiment, we show that all these three conditions are possible and can be achieved in our devices. So this establishes a platform to access Andreev bond state and potentially detect the topological non-trivial phase. Okay, so now the device architecture that we used is the following. So what we are doing essentially is that we have this sea of two-dimensional electron gas, which we are calling the normal region. And then on top, we attach these three superconductors, S0, S1, and S2. So without the gates, there are many conductance modes present between each of the three terminals. So to control the conductance modes, we attach these three gates that are shown in yellow that can deplete the 2DEG underneath them. So once that is done, the superconductors can only communicate via this central small region that can only support a few conductance modes. So the material platform that we use to realize this is this indium arsenide 2DEG that is epitaxially coupled to aluminum. So it has been shown that this forms a clean interface, and the superconductivity can be induced in this indium arsenide, and the superconducting properties can be controlled by this gating of this indium arsenide region. So we use this structure with three split gates on top, and our Josephson junction, three-terminal Josephson junction is formed by etching out this Y-shaped region. And everywhere else you have aluminum. So we made these devices. So we made two devices. So first I'll talk about device A that has a junction width of 200 nanometers. So here the junction width means the spacing between the two superconductors. So it's not really visible in this image, but if you really squint your eye, you can kind of see this Y-shaped region in the middle. So it's the width of that Y-shaped region that is 200 nanometers. And we have our three split gates, so that are labeled as VG1, VG2, and VG3. And we also have a central gate named VGC. So this central gate could potentially be used to do tunnel spectroscopy, but in this experiment, it is used to tune the electron density underneath it. So to control this three-terminal device, we use these two currents, I1 and I2. And first we look at transport properties when all the gates are set to 0 volts. So VG1, VG2, VG3, and VGC, they're all set to 0. And we use these two currents, I1 and I2, which are biased with respect to terminal 0 to control this device. And we measure two voltages, V1 and V2. V1 is between terminal 0 and 1, and V2 is between terminal 0 and 2. So once we do this measurement, it allows us to calculate this differential resistance map for dV1 over dI1 and dV2 over dI2, and also the cross derivatives. So we'll describe first the transport properties on this device in the dV1 over dI1 resistance map. So the first thing that one notices is the presence of these three superconducting arms. So there is this one, the darkest arm along this, and then you have two other faint arms along the other combination of I1 and I2. So first we'll describe why this line occurs and why does it occur where it does occur. So So this, the main superconducting feature is along I2 equals to minus 2I1. So one can think of this three terminal device as this network model where you have three nodes present at each terminal. So one, if you were to apply Kirchhoff's law at each node, then if you were to change I1 around this point, this junction between 0 and 1 would remain superconducting, thereby resulting in dV1 over dI1 equals to 0. So that's the story of this main superconducting arm. We also have these two other superconducting arms. So the second arm is around I2 equals to I1. So when I2 is equals to I1, again applying Kirchhoff's law at each node, we see that there is zero current between terminal 1 and 2. So that junction superconducts. And then if you were to change I1 slightly by amount dI1, then that access current only flows between terminal 1 and 2. So even though I1 has changed, the V1 does not change because that access current flow, because the current between terminal 0 and 1 has not changed. So that results in this lower resistance feature along I1 equals to I2. Similarly, you also get a feature along I2 equals to minus I1 over 2. That is when the junction between terminal 0 and 2 superconducts. And again, the access current flows through that. So you don't have a resistance, a voltage change between terminal 0 and 1. So that's the story of these three superconducting arms. We also see some faint lines enveloping these superconducting features. So I'll describe those lines in device B, which has a junction width of 50 nanometers, because these lines look even more contrasting in this device. And the reason being the junction width. So here the junction width is way less than the mean free path of indium arsenide. So it's less prone to scattering and more prone to resonances. So these lines look more contrasting in this device. And this device does not have a central gate, just the three split gates. So yeah, so we see these faint lines, and these lines are essentially due to multiple Andreev reflections happening in the device. So the lines that envelop the main superconducting arm along I2 equals to minus 2I1 are due to multiple Andreev reflections happening between terminal 0 and 1. And these lines happen to be along V1 equals to 2 delta over n, where n is an integer. And the lines that envelop this main diagonal along I1 equals to I2 are along V1 minus V2 equals to 2 delta over n, which is again the condition for multiple Andreev reflections. And one can also plot dV2 over dI2. And then we observe this multiple Andreev reflections along V2 equals to 2 delta over n. So we have this MAR happening between all three pairs of terminals. And along with that, we also see this quartet signal along V1 plus V2 equals to 0. So this quartet is a correlated set of 4 electrons. So these multiple Andreev reflections plus the quartet signal puts our device in the phase coherent regime, which is a necessary condition to observe Andreev bond states. So now we demonstrate the selective gating in device A. So to do that, first we set all the gates, that is VG1, VGC, VG2, and VG3 to minus 5 volt. And we receive this resistance map, which looks quite similar to the previous map we saw. So in this case, when all the gates are set to the same voltage, the resistance of all three terminals should be identical. And that's what we see. And then we sweep one of the gates, that is VG3, which is between terminal 1 and 2, to minus 6 volt. And we receive this differential resistance map, which looks quite different from the resistance map on the left. And the main thing to notice here is that the dependence upon I2 has decreased. The reason being that the junction between 1 and 2 is blocked now because of the negative gate voltage. So that doesn't allow I2 to affect V1 as much. And we get this map. And we also confirm this by doing network model simulation, where each Josephson junction is modeled by RCSJ. So in this network model simulation, we have 3 independent resistors, which are between terminal 0 and 1, and between 0 and 2 here, and between terminal 1 and 2 here. So when we change VG3, we only change the resistance R3. That is, we put R3 greater than R2 and R1, which are the resistance of these two terminals. And we get this map after by doing the simulation. And this agrees quite well with what we observe experimentally. So similarly, one can do this thing for the other two arms as well. So if we were to change the gate voltage on VG2, then it will modify the resistance between terminals 0 and 2 while keeping this and this resistance same. So that results in this simulated map, which again agrees with what we observe experimentally. And then one can sweep the gate voltage on this gate between 0 and 1. That changes the resistance between resistance of only this resistor and while other two are same. And that again agrees with what we observe experimentally. So here we demonstrate that each gate locally changes the electron density and doesn't affect the other two terminals, which is what one would need to tune the Andrea bond-state spectrum. So we demonstrate independent gating. The last bit is the regime of accessibility of the single mode regime in this device. So here we perform a 2-terminal measurement on this 3-terminal device. So we float one of the terminals and we bias the other 2 terminals by VSD, and you sweep this gate voltage on all the 3 gates on device B. And we observe that there is this supercurrent present up to the single mode regime. And there are these oscillations in this supercurrent and the multiple Andreev reflections that surround it. So these oscillations signify Fabry-Perot interferometry, which is a sign of ballistic transport between the terminals. And we are able to completely pinch off this device, as is signified by this high resistance region. And if we were to take line cuts along VSD, we see that the transport does indeed happen via a few discrete modes, as can be seen on this figure on the right. So this shows that the regime of this single mode, along with the presence of superconducting coupling, is accessible in our devices. And we obtain similar data for the other 2 pairs of terminals as well. So just to summarize what we did. So we show that the transport taking place between all 3 pairs of terminals is phase coherent due to presence of multiple Andreev reflections and quartet. And we show that we can gate each terminal of this device selectively, that is by not affecting the other 2 terminals. And also show that you can access the regime of single mode in this device along with the presence of superconducting coupling. So yeah, so these results establish these devices as a promising platform on which one can do Andrea bond-state spectroscopy or observe the transport signal of topologically non-trivial phases. So here are some of the experiments that we are currently doing or plan to do. So we would obviously want to detect the transport signal of topologically non-trivial Andrea bond-states and do tunneling spectroscopy as well by attaching the tunnel probe in the central region. And we could attach more than 3 terminals and then phase bias a pair of terminals to do phase sensitive Andrea bond-state detection. And the other interesting thing from this network model is that they can help us realize electrically coupled nonlinear oscillators. So yeah, that is the end of my talk. So yeah, any questions?
Yeah.
Okay.
Yeah. Thanks a lot for the talk. Now, I wanted to ask a question a little bit about the future directions.
Sure.
So you see, and I think it's maybe the first work where one sees mesoscopic effects in such a geometry. I may be missing some of the multi-terminal Josephson junctions, but this looks encouraging. Is it correct that right now you don't yet have evidence that there are states that would be coupled to all 3 terminals at once? And I'm not saying that there aren't any states. I'm saying you don't yet have evidence to support it.
Sure. Yeah. I think you're right in that regard, that we haven't yet made sure that there are that the coupling it is indeed taking place via central scattering matrix S, which is which has only a few, which can only support a few mode. But this experiment, one cannot definitely say that that is true. From this, it does look like that each pair is coupled by a 2x2 or n cross n superconducting matrix, which is, this giant block matrix, not complete coupling. Yeah.
And now the question is related to the circuit model and the quartets.
Sure.
So actually, I'm not sure. Did you see the recent paper?
Yes, I did. Yeah.
Right. So I'm talking about the paper by Gleb Finkelstein's group, and they claim that something I also overlooked, that this exact circuit would have a quartet response due to the nonlinear effects.
Yes, that is true, but yeah, I'm not sure how one can distinguish if it's due to exactly due to the circuit model or due to the actual 4E state.
Yeah, I also so it is indeed hard. So here's the question. Now, the dynamics of this model, of course, would produce a certain amplitude of the quartet response. Yes. And additionally, you do have a handle on the model parameters because you have a mostly what looks like a very decent correspondence between the model, between the simulation and your current maps. So yes. I was wondering if the amplitude of the quartet signal produced by this model would be comparable to the quartet signal that you observe or not.
Yes, so once we gate this device, as you can see that we don't really see these quartet lines anymore that are along this, you can see this faint structure entering through this, but we don't see that in the experiment. And yeah, I mean, in this simulation, these lines do happen to be where the model predicts them to be, like this line here. I mean, the model predicts it to be here. So yeah, it could be due to the circuit model itself, and may not necessarily be due to the 4E state that can happen in this device. But the idea is to completely pinch off these side regions and only have a central region and then redo this experiment. So we haven't been able to do that yet, but that's the plan. Yeah.
All right, thanks.
Mohit, I can pop up. I should say that I work in the group with Mohit and Gino, and so I've kind of seen the iterations of this talk multiple times, but I'm still, there's still all new things that I'm kind of learning. I know very little about this RCSJ model, but how many parameters are there in it that you can tune, to get your simulation and experiment to kind of match up like you do?
So you have 9 total parameters. So you have the capacitance, the resistance, and the critical current. So you have these 9 parameters that you can tune, and in experiment also you can tune all those 9 parameters. So you can kind of measure those parameters and feed them into the simulation, and then tune them a little bit to match your experimental results. Yeah.
Well, that's what I'm kind of curious. Like, what kind of dirty secrets do you have that you get these two things to match, right?
So the one important thing is that the values of the resistances and the critical currents that you measure in experiment don't always translate to the simulation. You kind of have to change them always, because the values that you measure experimentally are always hindered by heating effects and hysteresis, and the capacitance is sort of added to model that. So you do have to do a little bit of tuning, but there is not really a set pattern that, okay, if you get this, you do this, and then you simulate it. We kind of have to do hit and trial.
Right. Got it. Thanks.
Perhaps I have one additional question, and that is related to the asymmetry of the scans in the open regime, I think. So previously, here. So you see the scan is highly asymmetric, and I somehow remember that this doesn't actually contradict the system being time reversal invariant, but I forgot.
Yeah. So are you talking about this central asymmetry here?
Yeah, right.
Yeah, so this asymmetry is actually the result of a very small magnetic field that was present in the system. So this is not exactly at zero field, but there was a small field that we couldn't get rid of in the superconducting magnet that we had. But if you look at the result of this looks pretty symmetric because we were able to get rid of that remnant flux in the magnet.
So you're saying that the asymmetry of this scan of this scan is due to residual magnetic field.
Yeah, and this was shown conclusively in this other paper from Manachurian group from UMD, where they applied a positive field and then a negative field, and they were able to actually reverse this asymmetry. And in this fresh round of devices that we made, we are also able to do that by tuning the field from negative to positive, and this asymmetry actually reverses from negative to positive.
All right, thanks.
Yeah. Okay, so if there aren't any more questions, I'll stop the screen share then. Okay, so I guess that's it. Thank you everyone for joining today.
Yeah, thanks for the talk.
Okay,
Thanks, Mohit.
bye-bye.
Thanks for hosting, Anton.